So today we will continue the conversation about unsupervised learning, and we will continue talking about clustering. And I will start my lecture by briefly summarizing you what we've seen last time, which covered the discussion about k-means algorithm. And specifically, we would see what are the limitations of this algorithm and think how we can improve it in some ways. So this will be our introduction to the algorithm that I will introduce today, which is called k-midoids. And we will talk about this algorithm and what kind of new freedom this algorithm allows us to achieve, which k-means they didn't let us do. And then I would answer the question that many people are always thinking about clustering is how do we determine this k? How do we determine the number of clusters? So this will be our next question, determining the number of clusters. So I want to be honest up front, I would not give you a magic formula on how to determine k, but I will give you some consideration how we can be thinking about deciding about k and what different reasons you may want to take into account when you are selecting k. So let's first go back and think about general clustering problem. So what we've said last time is that whenever we are thinking about clustering, we start with some similarity or distance measure, and then we are defining the cost of the partitioning. Once we settle on the cost of the partitioning, we will need to have an algorithm which optimizes this cost, which finds the best partition according to this cost. And the cost that we introduced last time actually looked at both partitionings themselves, so from Cn to Ck, but it also introduced these representatives, Z1, Zk. And specifically, the course that we had did the following. It went through all the clusters from 1 to k, and then within each cluster, it measured the distance between the representative and the particular point, and computed the Euclidean distance between the two. So the algorithm that we've seen last time, the k-means algorithm, was working to find the best partitioning which optimizes this cost. And let me remind you the structure of this algorithm, because as I said to you earlier, the k-midoids algorithm that we are going to be using is actually a variant in some ways of k-means. So we started it first by randomly initialize Z1, Zk. So we already picked up the Z somehow randomly. So after the initialization, the next step for us is to continue iterations. At each point, we're going to come up with the new partitions and the new representatives, compute the cost, and if there is no change in cost, we can just stop. Otherwise, we continue iterations. So we're going to right now iterate until no change in cost. And for the first step of the algorithm, which is, we'll call it 2a, we will go for all the points in our set for I from 1 to n, and for each one of the points, we will find the cluster whose centroid is closest to this point. So in other words, we would say that Cj, the cluster, would contain all the points I such that Zj is closest to xi. So now for the fixed representatives, we reassign all the points, grouping them closer to the corresponding centers. The next step for us is to do reassignment of the reference points. So we will start for j from 1 to k, and we will make zj to be the centroid of the corresponding partitioning, which means we go and sum all the points of the partitioning and divide it by the side of that partitioning. And I belongs to Cj. So what we've done here, again, we summed over all the points and divided by the size of the partitioning. So it's like an average of all the points. So now let's look at this algorithm and think about limitations of the algorithm. The first significant limitation of this algorithm is the fact that the z's are actually not guaranteed to be the members of an original set of points x. So in this particular case, we may get another point. In some applications it's okay, in other applications it's really a concern. If we are thinking about looking at Google News and we created a representative of the cluster of the story which doesn't correspond to any story, we actually have nothing to show, and this will be really a problematic issue for many visualization applications. So we would ideally want to have an algorithm which actually gives us a freedom, if you wish so, to find the z's, to find a representative which is one of the original points. The second limitation of this algorithm has to do with the fact, again with a step 2b. In order for us to say that the representative is actually a centroid of the points, we had to utilize the squared Euclidean distance. And as you remember from the exercise that you did, that we can make the exact computation and see that if this is our cost function and we want to minimize it, meaning to compute the derivative, make it equal to 0, it will work this way only if the original functions that you are considering is square Euclidean distance. Now, in many applications of clustering, you want to work with other functions, not necessarily with square Euclidean distance. You may want to use L1 or something else. This algorithm will not cut. So you would need to come up with some other way to find the clustering algorithm which works with your metrics. So with these two limitations in mind, again, making a representative part of the original points and ability to work with any distance metrics, we are moving towards a new algorithm that we need to consider k-midoids. So we've done with summarizing k-means, and we can start now talking about k-midoids, which will resolve two of those constraints. So it's actually pretty good that on this board we can see both k-means and k-midoids. As I said earlier, k-midoids will be derived almost directly from the k-means algorithm. So let's see which parts of the algorithm are affected by the fact that our points, that our representatives are not part of the original points. So clearly when we are looking at step 1, in k-means, whenever we selected points, we can select any points on the plane, correct? In this case, because we want our points to be part of the original set, we can explicitly constrain the first step and say, you still have a freedom to randomly select whoever you want to be this representative, but do select it from the original set of points. This would be the first step that we may want to change. So let's write it down. We will say randomly initialize and we would again select this Z1, ZK in a way that they belong to our set X1, they are part of the set X1, Xn. So what we wrote down, that they have to be some subset of the original points. So now we selected our representatives to be part of the original cohort, and we can continue our iterative procedure. So we will here continue iterate until there is no change in cost. And let's look at step 2a. So in step 2a, every point had to go and find itself the closest representative. In this case, this particular step, first of all, doesn't limit us as to what representative could be, because we already selected them. And also it can work with any distance function, because as far as you can compute the distance between the representative and a point, it will work. So we can just directly copy the step 2a, which is building the partitions given particular representative directly from what we have before. So our step 2a will be for I from 1 to n, Cj collects all the i's such that Zj is closest to xi. So now the next step for us is actually go and select the new representative. And what we know, this is a place where all the action will happen, because in k-means, in this step, we were violating both assumptions. First of all, we were selecting the point, which may not necessarily be the member of the original set. And the second point is the reason our representative looked like a centroid was because we did this derivation and we directly built on the assumption that our distance metric happened to be square Euclidean distance. So here we would expect the change will happen, and let's just intuitively see what we would like to get in this step 2b. Let's say your cluster looks like something like this. In this instance, like the worst choice that you can make is to select this guy to be the representative of this partition, because the distance from these guys to all other points will be very, very high. So ideally you would select somebody from here which is kind of in the middle and close to all the points. So what we will do now is exactly right in the formula what I just said in words. We will go from one cluster, from the first cluster 1 to cluster k, and then we would say I want to select point zj, and this particular point is going to come from my original set, from my original points x1, xn. And what would I request from this point? I am going to select this point that if we are looking at the distance between this point and all the other members of the group, Cj, we would want this distance to be minimal. So we will select one of the points from our original cohort such that the sum of distances from this point to all the members of this cluster is minimal. So this way it will work with any distant function you may want to use, and also we don't make any assumption about this form because we explicitly are going to compute the distances between these points and the rest. So doing this algorithm, we for sure can solve the two problems which were limiting for us in the case of k-means. We can work with any distance function as far as you can compute it, and we also are guaranteed to get points from our original set. So what are the other interesting differences between these two algorithms? And one difference that you can see when you actually made this computation is this computation clearly seems to us more expensive than the computations that we are doing in k-means. So if we are to use capital O notation, which talk to us about the order of growth, let's look at this algorithm and compare them in terms of their time complexity. Now note that we don't know how many steps each of these algorithms will take to find us the partitioning, but what we will look at is the cost of one iteration of the algorithm, and then it will take many iterations until convergence. So let's start with k-means algorithm. So in this particular case, again, we're talking about the order of growth, which means that we're going to look at the asymptotic growth and eliminate all the constants. So we can see here that whenever we are doing both of this computation, they will cost us n, because we are doing it for every point, k, the number of clusters, and maybe multiplied by dimensionality d, which is the size of the cluster. So let me just explain what do I mean. So for instance, for stage 2a, you need to go for each point and find for it the closest representative. So the order of computation will be n multiplied by k, because you have n points and you have k representative. And the reason we're multiplying by d, because actually remember that our instances, our x's, may be very high dimensional vectors, and if we want to account for it, we can add it to our complexity. So this will be complexity for the k-means algorithm, and you can see that the similar complexity is achieved by the state 2b, but again, because we're talking about the asymptotic growth, whenever we sum them up, we're still staying within the same order of complexity. Now let's look at the complexity of the k-Midoids algorithm. So in this state, this step of the algorithm 2a costs exactly the same. However, here we are going to be paying much more, because now we need to compute the distances between every pair of points, and if we are using kind of straightforward implementation, the order that we are going to be considering is n squared kd. And I'm talking about the most naive implementation. I mean, there are ways to implement it in a better ways, but roughly speaking, however you're not going to implement, it's intuitively clear to us that this is more expensive computation, and for somebody it may be a decision to select one algorithm versus another. But at this point, we already have seen two clustering algorithms. There are hundreds of them available for your use. And the reason I wanted to show them the two, even though they're close to each other, they have different strengths and weaknesses. And whenever you are selecting clustering algorithm which fits for your application, you may want to think about different consideration when you're finding the best clustering algorithm for your needs. And now I would like to move, when we finished discussion about k-Midoids, I would like to move to the next question we have for today, is how we can determine the number of clusters. So let's go to this question. So we're talking about determining the number of clusters. And we call it k in both cases. Now, if you remember when I defined you what clustering is, I told you you're given points x and somebody gave you number k, and now your goal is to go and find me the best partitioning according to some cost. I never told you how actually to find number k. And for people who practically use clustering algorithm, this is a real question, because in most cases, you will not be provided with a number k. So let me first start by saying that in some cases, you may intuitively know what is a number k. So for instance, if you're teaching a class at MIT, you may be given 5 recitations, and you need to take your whole class and divide to 5 recitations based on some principle. So in this case, maybe you think you should be getting 10 recitations, but you have 5, you're limited by 5, and that's how you would assign, the number of clusters is given to you, and you need to operate within this reality. However, in many cases, you actually have some freedom in selecting the number k. Let's first look at the connection between the number k and our cost function. So what I'm going to draw you now is like a small graph here. So this will be number k. It's our number of clusters, okay? And this is the cost, okay? So the question is, how does k affect the cost? So if we put all our points in a single cluster, which means we have one representative, let's, to make it simple, talk about k-means. We have one representative, and then we have all these endpoints which are closest to it. So that's where the cost will be the highest, because now everybody, doesn't matter how far they are allocated, are compared against one representative. Now, if you are allowed to have, let's say, 2 clusters, it's already better, because now we have 2 representatives, and at least some points are would have their local center and will decrease the cost. So the cost is going to go down. And as we increase the number of clusters, we would expect that the cost would increase. And eventually, when every single point can be its own cluster, if we have n points, in this case, the cost would be equal to 0, correct? Because in this case, everybody has their own representative, the distance is equal to 0. So what we see here, that this is the relation between the cost and number of clusters. And now there is a question, how do I know what is the right k? And if you remember the example that I gave you about the cartoon and image quantization, we see that whenever we are making this choice, we are typically driven by the application. It's true that in this case, our cost of the partitioning becomes 0. But in the case of image quantization, it would mean that we don't do any compression, that every pixel stays as it is. It's represented by 24 bits, and we are not saving anything. Our image is perfect. We're not compressing it, but you're not saving any storage space. So the question for many cases would be, how do we value, in this case, the compression quality and the image quality? So let me give you some idea how we may do it if we have some task in mind. If you are just doing it for visualization purposes, you can try with different values of k and see if you like the picture, how it looks, if it provides you enough insight on the data. But in many cases, clustering, when it's used as part of the machine learning system, it can be a way to pre-process the data. And in that case, we actually do have a mechanism that enables us to select this number k. So let's assume the following scenario. Let's go back to what you've studied about supervised learning. You have some supervised learning task, okay? So you have your supervised learning task, and I'm saying supervised task. So here you have maybe some points plus, you have several plus points, and you have several minus points, okay? Let's say. This is your supervised learning. And in case of your supervised learning, you actually have very few points. I mean, you can train your classifier, and based on these points decides how your separator goes. But because you have very few points, you don't really know what is a good boundary, where to put the separator, correct? Because you have very few annotations. Now imagine to yourself that you also have large number of unsupervised points for which you don't know the label y, but you know that these points belong to this domain. you have some of these points. Now, intuitively speaking, if you can cluster these points and understand somehow what is the structure of these points, it may help you to better find where to put the separator in the supervised case. And one way to think about it when we are generating the features, we can, let's say, run our k-means clustering and then represent every single point here, not by its cluster, because it's not good enough representation, but let's say by its distance to the centroid of the computed clusters. So in addition to having the point itself, you also look how far it is located from the centroids of all the clusters. And now, in addition to however you represented the point x, you would also add some information which tells how geometrically it relates to all the pre-computed clusters. And in this case, if you do this type of representation, you can actually decide the number k based on your development data. You can say, if I do 2 clusters and I do this feature representation, then my performance on development is 75, but if I do 20 clusters, maybe my performance on the development is going to be 78, and that's why I want to do this number of clusters. So in this case, the k, the granularity of partitionings that you are getting, would be related to your performance on the final supervised learning task. And this is one way to think about it. So with that, we finish our unsupervised clustering part. And the last thing that I want to say is about the word unsupervised here. So people always feel that unsupervised means that we don't provide our system with any knowledge, that it's just, you give the algorithm runs and provides you the solutions. However, even though it's unsupervised in a sense that we don't provide any annotated points, we as people who develop those algorithms actually provide quite a bit of indirect supervision. We decide about which similarity measure to use. We decide about how many clusters to give. So this is a way in clustering where we can put our expert knowledge. And it's actually extremely important to design the similarity functions in a way which will produce you meaningful results. And if you're thinking about bag-of-words approach of representing text, these algorithms cannot figure out which words are more semantically important than other words. So it would be up to you to do some weighting for the terms so that the clustering results is actually acceptable. Therefore, we need to think very carefully how to do these decision choices so that our clustering is consistent with the expectation. And we will continue discussion about other unsupervised technique as part of the model about generative models.